Hello everyone. In the last two sections, we learned 4.4, which is spanning set, 4.5, dependent and independence. And right now, we are going to combine those two sections, and we are going to learn 4.6, which is basis and the dimension. So let's take a look. Okay. Firstly, I'm going to give you the definition and then show you the example. What the basis means. Definition 1, basis. Right now we have a set of vectors. So set of vectors, they are v1, v2 till vk. Okay, this is in general. And this is in a vector space. So the vector space sometimes can be R2, R3, sometimes can be matrices, right? Okay. A set in this one is called a basis for V if two conditions. The first one, the vectors are linearly independent. So just independent. The second condition, the vector span the vector space V. So I'm going to show you what's the meaning, okay? So independent means they cannot have any relationship. So this set should be the minimal set, cannot. We don't want to have like a kind of duplicate. For example, we don't want to have this kind of set because 1, 2 can be expressed by linear combination of those two, right? So in that case, you can see they are dependent, so we don't want to have this kind of thing. We only have the easiest set. So firstly, independent. Second, the vector span V. That means any vector in the set, in the vector space V, can be expressed by those vectors. For example, R2. For any R2, vector in R2, it can be expressed by those two vectors. They are like I and J, right? I vector, J vector. So any vector can be expressed by Ij, so Ij definitely spans R2. In this case, so here's the easy example. You can see actually 0, 1 and 1, 0. Sorry, I made a mistake here. So let's write down 1, 0 and 0, 1. This is I, this is J, this, okay, they span R2 and they are independent. So we can see, actually, we can just say Ij is a basis for R2. Okay, that's the meaning of basis. And actually, definitely we can think about what is like R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is a basis, right? Because they span R3 and they are independent. So this is a basis for R3. And they are called standard basis because they are the easiest basis. There may be some other bases like different vectors, but they are just called standard. Okay, now let's take a look at the example 1. Example 1, we want to find the standard basis for M2R. So let's see. Determine the standard basis. So standard usually means easiest, okay, simplest. M2R. So M2R means what? Any 2 by 2 matrices with all the elements in R. Real number with all the real number elements, right? So let's take a look at this one. The general like matrix in R2 is So let's see. The general or any matrix, okay, matrix in M2R is what? Usually we just write down like A, B, C, D, and the A, B, C, D, they can be any number. And let's see. Actually, for the A, B, C, D, we know this can be expressed by linear combination of 4 vectors, right? So do you know how to write down those 4 vectors? Although those 4 matrices. So let's see. A times 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So any matrix can be expressed by linear combination of those things. So that means if we say this is A1, this is A2, this is A3, A4. So we know they span R2. Is that correct? They span. Because any vector, any matrix can be expressed by those 4. So for the basis, we want to find the basis. So this means span, okay? And for the basis, what do we need else? For the basis definition, span and independent, right? Independent. So how to prove they are independent? Looks like it can be basis, but we need to prove they are independent. So for the independent, we just set linear combination of all those 4 vectors. Solve for C. Make them equal to 0, right? That's the definition for independent. So we want to see is dependent or independent. Okay, we want to see which one. Now we can combine the left side. When we add all those matrices together, we get what? C1, C2, C3, C4. Actually, and this equals 0, 0, 0. What that means? That means all the C have to be zeros. If they are all 0, for the linear combination, if we can only find the 0 C, that means they are independent, right? So in this case, we prove the span and the independent. So what A1, A2, A3, A4 is a basis for M2R. Something like this. I can give you one exercise and you can think about for this subspace, which is given by this one, okay? This is all the A belongs M2R, but all the matrix equals upper triangular. That means this position is always 0, upper triangular, okay? And it's 2 by 2. And here, A, B, C belongs to R. Let's find a basis. You can try to find the basis for this one. Actually, you can see any matrix can be expressed by what? A, 1, 0, 0, plus C, like this one, right? Any matrix can be expressed by those 3 combinations, so they span, okay? The first thing span, those 3 like A1, A2, A3 span the subspace S. Next, we want to show they are independent, so we see independent means what? C1, C2, C3 equals 0. And from here, we can definitely get C1, C2, C3. That means all the C equals 0, so independent. So what's the basis for this subspace? The basis should be just A1, A2, A3. Right, this is a basis for S. Okay, this is the first exercise. Second exercise problem. Think about P2. P2 means what? All the polynomial with degree 2. So we can write down A0 plus A1x plus A2x squared. So all the function, all the polynomial has this, and all the coefficient are constant. Right, so this is kind of like set notation for P2, means all the polynomial. So we did this before, spanning in 4.4 spanning set. Who span P2? So P2 is spanned by 1x and x squared. Right, these spans are P2 because any quadratic polynomial can be expressed by linear combination of those three functions. Next, we want to see if this is basis or not. So we just need to test is dependent or independent. And their functions. In 4.5, we learned how to test dependent or independent of functions, right? So we do which way? We do Wronskian. Do you still remember this one? Means determinant of this thing. So 1, 0, 0, derivative 1, and derivative 2x, here's 2. Calculate this determinant. So this should be, we expand by use first column, so it should be 1 times 1, 2x, 0, 2. So the answer should be 2 is doesn't equal 0. So if the Wronskian is not 0, that means they are independent, right? So actually 1x x squared is a basis for P2. Okay, so here we did a 2 exercise, 1 example. Here I can give you like a more general. So what's the standard basis for Pn? What is Pn? Pn means all the polynomial with degree n. That means, so for quadratic it's 1x x squared, right? So for Pn it's 1x x squared and till x to the power n. Okay, 1 means like a constant because all the polynomial has constant, and this is the highest power, xn, and they are independent also. Now let's take a look at the definition 2. In this section is called basis and dimension. So second part is going to be dimension. Definition 2. Let's see the dimension of A space V, okay, of a finite dimensional space V, so denote by this one, written as DIM and the bracket V. Okay, this is a notation for the dimension, and it's the number of the vectors in any basis. Is the number of vectors in any basis. What's the dimension? Dimension means number of vectors for V. Okay, so if the vector space just has one vector, like 0 vector, then we define the dimension is 0. That's special case. Usually the vector space is not 0. Let's take a look at what's the dimension for R2. For R2, we know what is the basis, standard basis IJ, right? So this is the basis. So you can see how many vectors? 2 vectors. So that's why we always call that two-dimensional space. Same thing. And you can see what is Rn. R3, let's do R3. Should be 3, right? 3-dimensional because IJK is the basis. So in general, Rn is n-dimensional space. And let's take a look at the dimension of M2R. Do you remember what's the basis for M2R? 1, 0, so like A1, A2, A3, A4, right? In the first example. So dimension should be 4 here. How about the dimension of P2? P2 means all the polynomial, quadratic polynomial. The basis actually is 1x squared. So how many vectors here? Dimension 3. So same thing, P3 dimension, which is 4. And the dimension of Pn should be what? Think about that. In a remark, how many bases there? N plus 1. Right. Okay, so let me just give you the conclusion. Dimension of Rn is n. Dimension of MNR is n squared. So like 2 by 2 means 4. And the dimension of M by R matrix, dimension is M by R. It's like M rows and columns. And the dimension of Pn means all the polynomial with degree n. So that is n plus 1. Okay, that's the dimension. Now let's take a look at example 2. Determine a basis to the solution of differential equation. So let's see. Determine a basis for the solution space or solution set. Actually, the solution set is a subspace, so that's why it's called the solution space to the differential equation. And the differential equation looks like this. Second derivative plus y equals 0. Okay. Right now, we don't need to know how to solve this differential equation because it's second order differential equation. We will learn this in the next chapter. Okay, but here I just give you the solution. The solution to this one is actually y equals c1 cosine x plus c2 sin x. This is a solution set. Okay, and this is a solution. So if any solution is a linear combination of those two functions, so you can see which two functions, sine and the cosine. So we can write down them together. This spans the solutions space, right? And next, if we want to like prove they are independent, so we just write down the determinant sine, cosine, derivative which is cosine, derivative of cosine should be negative sine, and after simplify, negative sine square minus cosine square, so which is negative 1 if we simplify. This definitely is not 0, so independent. In this case, we can see span independent, so sine cosine is a basis. So sine cosine x is a basis for the solution space. That's why we want to learn all those kind of stuff, independent, span, and the basis, because in the future we are going to solve all the differential equations, and we just want to have a simplest solution set or minimal solution set. So that's means all the solutions can be expressed by sine, cosine. So all the solution has property of sine, cosine. That's all. Let's see. This solution set has dimension 2, right? So this solution set, if we say this solution set is S, so dimension is 2. Now let's take a look at example 3. Verify that this set is a basis for P2. One plus x, 2 minus 2x plus x squared. 1 plus x squared is a basis for P2. Okay? So we know the P2 has dimension 3, right? Dimension of P2 equals 3. And here we have 3 vectors. It can be a basis, but we want to prove. Okay? We need to prove. So we need to prove they are independent. Okay, they're independent. Let's see how to prove they are independent. Wronski. 1 plus x. We also did this in the last quiz. 1 delta 1 0. 2 plus 2x, and here's 2. 2x delta is 2. And we can, after simplify, this one equals -6. We skip the detailed calculation, but you can simplify, use this to make that into 0. Okay. And this doesn't equal 0, so we know independent. They are independent, so we know F1, F2, F3 is a basis for P2. Let's see. We can try this exercise. Yes. 1, 2, 1. A basis for R3. Is this a basis for R3? So we know that R3 has 3-dimensional. Three-dimensional space, and here we have 3 vectors. We want to show they are dependent or independent, right? So for the independent and the dependent, to use 3 number, we set A matrix, so A, and calculate the determinant. So it's like AC equals 0. Solve for AC equals 0, and this linear system has 0 solution or non-zero solution. And the column made by the vectors, so like V1, V2, V3. Let's write down the A. Okay, so here's the exercise. I'm going to use the blue color. Calculate determinant. The determinant of this one, simplify a little bit. Use this one, make others into 0. So it's going to be this, and use this times this one, so it should be 14 minus 1, which is 13. Non-zero, independent. Right, independent. that means there's only 0 solution. Okay. That's the exercise solution. Now we still have the last example. So you can see here for the basis and the dimension, we did some like for R2, R3, P2, and we also did some solution set to linear differential equation. Next, we are going to do matrices. We also did this in the first example, right? But let's see. It's kind of like duplicated, but let's just do more. Let S equals to this set. Firstly, all the matrices belongs to 2 by 2 matrices, and AT equals A. So what's the meaning of AT equals A? Symmetric, right? We want to determine a basis. So what's the symmetric matrix look like? We can do A, B, and then here has to be B. Is that right? So those numbers have to be the same thing for the symmetric matrix. So all the matrix has this kind of form, and we can write down this as what? A 1 0 0 0 plus B times what? So you can see 0 0 0 1 B times 0 1, because we have 2B here, so here also have B 1 0, right? So those three A1, A2, A3 matrices, they span this S subspace. Okay, span this S. So this can be a basis. So we know here 1 0 0 1 0 A2 and A3 spans S. Next, we need to show they are independent. Okay, independent means C1, C2, C3 equals 0 0 0. And definitely it's easily you can see when we combine the left side, C1, C2, C3 have to be zeros. So that means they are independent. Span independent, so this is the basis. Actually, that is basis. So the basis is one zero 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 0 1 1 0 and 0 0 0 1. And then if I ask you more, like what's the dimension? 3, right? Okay, that's all we need to know for this section. So summary, we need to know what? The first thing we need to know what's the definition for basis. Basis means satisfy two conditions, span and independent. So sometimes the vectors can be polynomial. For independence, we do Wronskian, right? So like W, F1, F2, those kind of things. And if vectors, we do determinant of the matrices. We want to prove they are not equal. Or sometimes we just do like a linear combination for the matrices and equal 0 0 0 and solve for C's. So for independent. For span is 4.4. We just need to know any vector can be expressed by the basis vectors. Second thing we need to know is dimension. Dimension means the number of the vectors, right? So the number of vectors in basis. So we did several examples here. You can try the homework problem, and that's all we need to know for this section. Thank you.